There we go. All right. So just a reminder, I will not be here on Friday. I will not be here on Monday, and I will not be here next Wednesday. But I should be around for, you should be able to email me if you guys are running into a problem. So where we were on Wednesday is we had talked about impulse, right? That was my force times my change in time is going to equal my change in momentum. And we showed that different parts of that and how it came to the Newton's second law. I do have some videos that I will be posting for you guys because in my normal class I can actually do a demonstration of this, but I have a video that actually shows the demonstration. But we look at the force versus momentum. In our text, our author chooses to remind us at this point that if I want to look at center of mass of systems, I want to go in and make sure that my center of mass and looking at it is going to be the sum of the masses times each individual x divided by the total mass. Or if I do it in y, I can do it this way for the y component, and I can do it for the z component. And this is written out as if I'm doing this kind of center of mass problem. Okay? Where I have 3 items. I know where these locations are. So let's go ahead and say this is 3m, this is 2m, and this is just m. This we'll say is located at 1, 1. This one we'll say is located at 4, 3, and this one we'll say is located at points, or let's see, we'll say that this is 3 and 0.75. So I've got those 3 points, and we want to find the center of mass of this system. So if I do that, I can actually find the center of mass of that system. So if I want to do the x center of mass, it's going to be mass 1 times its x location, mass 2, which was 2m times its x location, and mass 3m times its location. All divided by the sum of the masses. So this is mass 1, 2 masses, it's going to be 3m, 3m, that's going to be 6m as my total mass. So I'm going to have 1m plus 6m plus 12m divided by 6m, which is going to give me 1819m divided by 6m, which is going to give me 19/6, which is going to be something like 3.33 if I get it right. Something along those lines. 1/6, no, it's going to be like something like 1/12-ish. That's where the x location was going to be. So it's going to be a little over here along this line, somewhere in between these 2 big masses. And then I can do the y component, and that's going to be m times 1, m 2m times 0.75 plus 3m times 3, all divided by 6m. So it gives me 1m plus 1.5m plus 9m divided by 6m. It's going to give me 11.5 divided by 6 is going to be my result, which is going to be a little less than 2, right? I'm going to be pretty darn close to 2, so I can say about 2. So if I'm plotting this, we've got there, and this is about 2. My center of mass for this system is going to be somewhere right in there if I were doing this. And the first time we encountered center of mass was when we were looking at gravitational attractions. So I could have a 3-body system, say these are 3 asteroids that are rotating around each other, and I'm looking at it around the sun. How that center of mass is interacting with the sun was how we actually looked at it, and our author tried to bring that information out at that point. But this is the chapter that our author chooses to do something a little different, that we now can add the calculus to it. So if I have a stick, meter stick, if I do x center of mass and I do the sum of the masses times x divided by the total sum of the masses, that actually can be written, and we've seen it, as x, or as x dm over the entire mass. So I can do this in small integral form. So if we do this, we can go from 1 to L. I can use a linear density, mass divided by L. And if I'm doing an incremental little piece, right, this is dx, my dm is going to equal my mass L dx. So I can put that into my equation here. We know what this is, right? We know that that's just going to equal total mass. So now I can do 1 over the total mass, the integral from 0 to L of my lambda dm, but my lambda dm is equal to m over L dx, and I have my x out here. So now I get 1 over L, because my masses cancel out because I get m over m, and I integrate from 0 to L x dx, and hopefully you guys have that one by now, right? So I ended up with 1 over L x squared over 2 evaluated from 0 to L. And if this is a uniform mass across there, this is going to be L divided by 2 is where my center of mass is going to be, which you guys intuitively knew already. But we can do this in other dimensions as well. I have a triangle. I can do a density of my triangle. This is an area density. So this is going to be divided by the mass divided by my unit of area. Right? My mass divided by the unit of area. And if I give this as, we're going to do this as, we're going to give this as H, and we're going to give this as B. So my X center of mass is going to be, so my dm that I worry about is going to be my row area dx. And so I can go from 0 to B, row area x dx divided by row area dm. But we know what that is. That's 1 over m. My row area is m over a. And I'm going to integrate x squared or x dx from 0 to b. But my area of my triangle is what? Area is 1/2 BH. So now I get 1 over the area, because my m's will cancel, and I'm going to integrate x squared over 2 from 0 to b, and I end up with 1 over 1/2 bh, and I get b squared over 2. That's still not coming out right, because this should end up as 1/3 b, because we know it's going to end up right there. I've set this up wrong somewhere. I was playing with it before lunch, and I keep missing it where it is, because we end up with 1/3, because we know it's going to end up with 1/3 here, and we know it's going to end up with 1/3 there for a triangle. But you guys have been playing with this in calculus. That's also why we have lots of lovely tables. So you can play with that a little bit. I will leave it to you, because we got to cover a couple more pieces here. So let's look at momentum. Why our author throws this in here at this point, I'm not quite sure, but I wanted to make sure that you guys had it so you could actually work the problems. Oh, so let's do this one first. I've got a system that's going to go off at 0.35 meters per second. And that's a 60-degree angle. This one is going to be a 30-degree angle, and it's going off at 0.45 meters per second. This one's going off at 0.25 meters per second. And this one's bouncing back at 0.5 meters per second. So this is essentially after the cue ball breaks. All right, so this is, we've broken the initial shot. Each mass is going to equal 1.61 kilograms. We want to know the total momentum of the system. So in this case, we're just calculating momentum. Except, I got to account for angles. Okay, this is not just in the x direction. It's not just in the y direction. I have to account for angles. So I want to calculate the total momentum of the system. So the way I do it is I look in the x direction. So we'll start out in the x direction. This is going to be the mass of ball 1, velocity of ball 1, plus mass of ball 2, velocity of ball 2, plus mass of ball 3, velocity of ball 3, plus mass of ball 4, velocity of ball 4, is going to give me the total momentum. And if I do this, if I'm going to go ahead and just go give you all of this, this is irrespective of the dimension. If I'm doing just the x direction, I'm only worried about the velocity in the x. It's going to give me the total momentum in the x direction. Good news for us is all the masses are the same, so we can filter things out. So I'm going to get the mass times my x component of each of the different balls. So in that one, I have to keep a track of my direction. So I've got 0.5 meters per second. X direction, this one has none in the X direction, so I've got a 0 there. I've got this one, which is going to be my 0.35 cosine 60 degrees. And I've got this one, which is going to be my 0.45 cosine of 30 degrees. It's going to give me 0.16. And if I do this, if I take my 0.5, put these into the calculator, I get 0.065. And this, my units are in kilograms, meters per second. Kilograms, meters per second. And that's, when I get it all totaled up, it gives me 0.010 in the X direction. I can do the same thing for the Y direction. This one has 0 in the Y, it's only in the X. Okay. It's got 0 in the Y, only in the X. That one has me a negative 0.25. This one has a positive 0.35 sine of 60 degrees. And this one has a negative 0.45 sine of 30 degrees. That gives me 0.16. And I got my negative 0.25. And I can add in these other ones. .35 times sine of 60. This is plus 0.303. That's minus 0.225, which gives me, when I plug it all together, 0.028 in the Y direction. Now, depending on how WebAssign actually wants the value for the total momentum, I can do it like this, that the momentum vector is going to equal 0.010 in the I. That should be a minus 0.028 in the J. Or I can do the magnitude of the P vector, which is the square root of 0.010 squared plus 0.028 squared. And that gives me 0.049, and that's in kilograms, meters per second. Oh, but let's do something fun. These are the fun types of problems. That skin is starting to die off. Okay, we're going to assume a frictionless surface. And we got a box on a frictionless surface. And my box has a mass of 25 kilograms. It's sliding down our surface at 6 meters per second. This is a 30-degree angle. And at the bottom of the chute, it's going to hit the sled. And the sled is going to go off with a velocity that we want to calculate. And our sled has a mass of 50 kilograms. So we're going to use momentum to help me figure this out. We've got conservation of momentum, so the momentum before has to equal the momentum after. So what's going to happen here, and we know what happens, the box is going to hit this, so I'm going to need to know the x component, because that's what the x direction is where things are going to happen. So we are going to need the momentum in the x direction of the box, and that's going to equal the momentum of the box and sled after it comes off the sheet. So I'm going to have the mass of the box, which is 25 kilograms. I'm going to have the velocity of the box, but at 6 meters per second, cosine of 30 degrees is going to equal the mass of the box plus the mass of the sled and the new velocity that we're looking for. So in this case, I'm going to get, this works out to be about 130 kilogram meters per second. My box is 25 kilograms. My sled is 50 kilograms. Times the velocity that we don't know. So I'm going to get 130 kilograms meters per second divided by 75 kilograms. And that's going to give me 1.73 meters per second that the sled is going to go sliding off. Everybody has watched the old World War II movies and seen Big Bertha. Everybody know Big Bertha? Big Bertha is a railgun. So we've got a big railgun. And one of the things that we saw when Big Bertha went off, besides the compression of the cannon this way, we end up with the cart going that way. Good old recoil. Okay, good old recoil. So let's say that we have a railgun that has a mass of 70,000 kilograms. We're going to fire a pretty significant shell, 500 kilogram shell. This is going to be an angle of 45 degrees. It's going to leave with a muzzle velocity of 200 meters per second. Okay. And we want to calculate the recoil. So we know that the momentum before has to equal the momentum after. This is initially at rest, so my momentum before is 0. Now my momentum after is going to be the mass of the shell times the velocity of the shell plus the mass of the gun, velocity of the gun. Well, I know the mass of the gun, I know the mass of the shell, I know the velocity of the shell, I don't know the mass or the velocity of the gun. That's what I'm trying to figure. Now, we know that this is going to go in the other direction in order to have everything move out, so this actually has to be negative because I'm ultimately going that direction. So I'm going to end up with the mass of the shell, velocity of the shell is going to equal the mass of the gun, velocity of the gun. If my picture is drawn right, my arrow will end up being positive for the answer here. So my mass of the shell divided by the mass of the gun, velocity of the shell, is going to equal the velocity of the gun, which now means that my shell is 500 kilograms. The gun is 70,000 kilograms. The velocity of the shell is 200 meters per second. And if I do the calculation, oops, I have to account for the angle. So that's 200 kilograms cosine 45 degrees. And if I do that, this ends up being about 1 meter per second. And if anybody's ever fired a shotgun, you know we got recoil.
New ones don't.
Huh?
New ones don't.
They still have recoil.
I mean, they do, but you don't feel it as much.
They still have recoil. They all have recoil. It's got to go somewhere. All right. So we have finished chapter 9 or chapter 10 or whatever chapter it is we're in. We're about to start the next chapter, which is all about collisions. The same things as well. Let me do one. I can do this one off the top of my head. We'll deal with a lovely Volkswagen Beetle. We'll crush a Volkswagen Beetle.
So this is like the Bedlam assignment stuff.
Yeah. This is like the Bedlam assignment stuff. So I want to make sure you have the capability of looking at it. So here's my good old train, right? So I got my train cow catcher. Okay, now a couple things for working these problems. An inelastic collision, conservation momentum. Okay, elastic collisions, a special case. You have conservation of momentum. But you also have conservation of kinetic energy. So it is a special case, and so if you're working homework problems along the way, elastic collisions are a special case of collisions. I have conservation of momentum and I have conservation of kinetic energy. Of course, my train and my car crashes are all inelastic collisions, and that's what you're going to be working with. So if I start with it's just a diesel engine, let's go ahead and give it 70,000 kilograms, which is not an unheard of size for a diesel engine. If I take my Volkswagen Beetle, okay, Volkswagen Beetle's roughly 2,000 kilograms. Actually, it's a little heavy if that's 2,000 kilograms, but we'll say 2,000 kilogram vehicle. We're going to make the assumption that things work out perfectly, and the Volkswagen Beetle on the after side just ends up here on the cow catcher. It doesn't smash up into a gazillion pieces. It will smash up into a gazillion pieces in real life, but we're going to, just for grins and giggles, we're going to say that we got lucky and the car just scooped up and stayed on the engine. We're going to do that the engine's coming in at 27 meters per second, roughly 60 miles an hour. We want to know the velocity after the collision. Okay? Velocity after the collision, which is why the train always wins. Okay? The train's going to always win this battle. Okay, momentum before is the mass of the train, velocity of the train, plus the mass of the car, velocity of the car, is going to equal, at the end, we said it's scooped up. So now I've got the mass of the train plus the mass of the car, the velocity after. Okay? Everybody with me? Momentum before is equal to momentum after. So now if I plug in numbers here, I get 70,000. Velocity is 27 meters per second. That term is 0 because the car is just sitting there. Divided by the combined mass, which is going to be 72,000 kilograms. This is kilograms. I end up with we're going 26.25 meters per second. The train didn't slow down a whole lot. And if you think of the train, and that's just the engine. If I have multiple cars after it, the train doesn't even know it hit something. Doesn't work so hot. Now, if I have a car and it's coming in, and we'll be nice. We'll say it's coming in at 18 meters per second, and it's going to collide with another vehicle. And this one let's say this is a truck, so it's at about 5,500 kilograms. This is a nice little Fiat, again about 2,000 kilograms, and we'll say we'll give it a little bit of an oomph. We'll say it's traveling at 20 meters per second. We come to the intersection, they lock up, they're together, we've got to smash this way, and they skid off together like that. So we're gonna make the assumption that it's a totally scrunched up. They're gonna go off at an angle and a velocity, and we want to figure that out. The way to look at these is I can create a table. I've got an X direction and I have a Y direction. Mass comes in here, the mass of the truck, velocity of the truck is in the X direction. And now I have the combined truck plus car, velocity, cosine of the angle. This is the before side, and this is the after side. This one becomes the mass of the car, velocity of the car, mass of the truck plus mass of the car, velocity, sine of the angle. Now I can use my algebra trick, right? Where I can take the mass of the car, velocity of the car, divided by the mass of the truck. Velocity of the truck is equal to the mass of the truck plus the velocity, mass of the car, velocity, sine of the angle, divided by the mass of the truck, plus the mass of the car, velocity, cosine of the angle. These terms cancel. That equals the tangent of the angle. So now I've got my car is 2,000 times my speed, which was 20 meters per second. My truck is 5,500, 18 meters per second. If I do that on the calculator, I end up with 0.404, which is equal to the tangent of the angle. My angle equals 22 degrees. Now I just plug it into one of those. So we'll do the truck. So I get mass of the truck, velocity of the truck, divided by the combined mass, mass of the truck plus mass of the car. Cosine of 22 degrees is going to equal the velocity. So that equals 5,500, 18 meters per second. 5,500 plus 2,000 is 7,500. Cosine 22. This gives me 99,000 on top. This gives me 6954 on the bottom. We end up at a velocity of 14.2 meters per second. So these would be sliding off at 14.2 meters per second at an angle of 22 degrees if those collided and gravitated together.
Is that exactly what you want, like the police report problem? Someone like
That's
that?
something like this is what you're looking at.
Okay.
But remember, this makes the assumption that these two stuck together completely.
Yeah.
And this also disregards friction. Which is also why I gave you the police report extra sheet.
It would change if it was raining outside too, I think.
Well, that changes your friction. That changes your friction. All right, so you got plenty to work on.